Hello everybody. We have discussed about optimum source coder, which is producing source codes with high efficiency and less coding delay. Now we have to think of error-free transmission. Suppose we have two messages M1 and M2 and they are encoded as 0 and 1 respectively. If we transmit these messages directly, then it is possible that on the receiver side, we may not receive the correct data due to noise and distortion in the communication system. Receiver is also not having any mechanism to detect or correct the error and complete information loss may occur. Suppose we transmit M1 message by 000 and M2 by 111 instead of transmitting by simply 0 and 1 respectively. Now in this case, if 1 bit error is there, then still the receiver can decide the message correctly. But receiver will not be able to correct the error if there is more than 1 bit error. If there will be 2 bit error, then receiver will not be able to correct the error, but it can find out that some error is there in reception process. It means the receiver can detect the error but not able to correct it. This example of introducing two redundant bits is giving capability of 1-bit error correction and 2-bit error detection. But at the same time, the delay is rising along with the channel burden. Since we are transmitting 3 bits instead of 1 bit for the same message, effective information rate is decreasing. If we transmit message M1 by 5 zeros and message M2 by 5 ones, instead of transmitting by simply 0 and 1 respectively, then receiver will be having error correction capacity of 2 bits and error detection capacity of 4 bits. But the information rate will be reduced by 5 and coding delay will also increase. So we have seen that as we are increasing the number of redundant bits with the information, error detection and correction capability at the receiver side is increasing, but at the same time, information rate is decreasing. We have an optimum source coder which encodes HM bits per symbol with zero redundancy. It means we are going to transmit hard information. This is risky as any noise or distortion in the channel will lead to information loss, as well as receiver is not having any capability to correct or detect the error. Now, as we have seen that if we add some redundant information or bits and that is transmitted along with the information, then complete information loss can be avoided. These redundant bits which give error correction or detection possibility to the receiver are termed as parity check bits. If we are adding one check bit with the information, the length of the code will increase by 1 bit and thus the efficiency of the code will also decrease. We came to know from the previous discussion that by adding some redundant bits to the information, we can provide error detection or correction capability to the receiver, but at the cost of efficiency of the code. In source coding, we learned that we need to remove redundancy from the code generated by the source by using optimum source coding technique. But here, to combat noise, we are adding redundant bits. In source coding, redundancy is unwanted, but in channel coding, addition of redundancy is desired to have error-free communication of information. Here, a question comes in our mind that how much redundancy we need to add or we require. It is very clear that more the redundancy, better the capability to combat the noise. But at the same time, coding delay is increasing. So we cannot add infinite redundancy to the information. This redundancy depends upon the channel capacity. We'll talk about channel capacity later. Suppose we have transmitted binary information. Probability of correct decision is P, thus the probability of wrong decision or error probability will be 1 minus P. Then capacity of binary symmetric channel CS will be given by the formula mentioned. Here CS is a number and it is less than 1. Suppose CS is 0.4. It means that if we transmit 1 bit, then 0.4 bit is information and 0.6 bit is redundant. It means that length of the code will be 2.5 times the entropy of the source, and we need to add 1.5 redundant bits with every bit of information. So CS conveys how much redundant bits we should add. From here, we can also say that if the capacity of the channel is 1, then channel is perfect and redundant bits are not required to embed with the information. As per classical theory, we have seen that if we want error-free communication, then from the error formula derived using bank of correlators states that the ratio of bit energy and noise should tend to infinity. But Shannon proposed that error-free communication of information can be achieved, even with finite amount of transmission power and presence of noise, with finite data rate if information rate is less than channel capacity. This is already known to you that if bandwidth of the channel is B, then we can transmit the symbols at the rate twice B symbols per second. Then channel capacity will be equal to twice B times CS. Channel capacity is not attribute of the source. It is attribute of the channel only. Channel capacity means that we transmit twice B symbols per second and with CS bits of information with every symbol. We know that if bandwidth of the channel is B, then we can transmit symbols at the rate of twice B symbols per second without any inter-symbol interference. Shannon said that if information rate is less than the channel capacity, then we can have error-free communication of information. Here channel capacity is property of the channel and it will be different for different channels. Hamming suggested that the distance between the two digital codes is a measure of difference in their bits. If two messages differ by 1 bit, then Hamming distance between the messages is also 1 bit. If we assign code words, then neighboring vertices should not be assigned as code words. For example, if code word is 000, then 001, 010 and 100 cannot be other code words. Let us take an example that we have to assign code words to the messages and we want n-bit error correction capability. Then length of the code word should be 2n plus 1 unit. Suppose the circles drawn keeping message at the center with radius of n units, then all the circles should be non-overlapping. For simplicity, we can take two messages M1 and M2, and if we transmit by simply 0 and 1 respectively, then 1 bit error occurs and complete information loss will be there. Now suppose messages are transmitted by 00 and 11. Then if 1 bit error is there, receiver can say there is error, but it cannot be sure about the error and cannot correct it. It means it can detect the error but cannot correct it. Take another example that messages are transmitted as 000 and 111 respectively. If 1 bit error occurs, then receiver can easily decide the transmitted bit and correct the error. Similarly, if we want 2 bit error then length of the code word should be 5 bits. That is, messages M1 and M2 are transmitted by 5 zeros and 5 ones respectively. Thus, if we want n-bit error correction capability at the receiver, then we need to have two n plus 1 bits in the code word. It means if we draw a circle around the message of radius n bit, then both the circles will be non-intersecting or non-overlapping. For error detection of n bit, we need to have length of the code word to be n plus 1 bits. If we keep on adding the redundant bits, the probability of wrong detection decreases. But this is not satisfying the Shannon's theorem, as effectively the information transmission rate is decreasing. In the previous example, as we are increasing the redundant bits, error detection and correction capability at the receiver was increasing, but effectively we were decreasing the information rate. So if we can have group of bits and we can add few check bits to find the error in the group of bits, then it will be better rather than guarding only one bit. Let alpha be the binary information bit rate. Now we take a group of bits accumulated in t seconds. Then number of information bits accumulated in t seconds will be alpha times t. Now we add some check bits and let beta t are the transmitted bits. Then beta minus alpha times t will be the number of check bits. In a binary symmetric channel, number of messages of length alpha t will be 2 to the power alpha t and number of possible transmitted messages will be 2 to the power beta t. There are 2 to the power beta t vertices in corresponding Hamming hypercube in a space of beta t dimension. Fractional occupancy will be defined as the ratio of code words to the total words. Here we have 2 to the power alpha t code words and 2 to the power beta t number of total words. We can also find out that the reduction in information rate will be the ratio of number of information bits to the number of transmitted bits, and that is alpha by beta. When the ratio alpha by beta is nearly equal to 1, then reduction factor will be nearly unity. So if beta is slightly greater than alpha, then information rate will not suffer high and error correction or detection capability will also be provided to the receiver. In other words, we want non-overlapping Hamming sphere at minimum distance apart. We can say that if we want 2 to the power beta minus alpha t tends to infinity, then also that beta is slightly greater than alpha, then we need to have time t tends to infinity. This means that we need to increase the time t, and that is more number of bits in a symbol. But this is not solving our purpose, as we are increasing the time. Coding delay is also increasing proportionately. So there should be some limit on beta such that it cannot be less than some value for given value of alpha. It means we have to sacrifice some information rate. In a binary symmetric channel, suppose PE is digit error probability. If beta t are the number of transmitted bits, then number of error bits in the sequence of length beta t are beta t times PE. As t tends to infinity, that is number of trials to be very large. This signifies that we must leave all the vertices unoccupied within the spheres of radius beta t times PE around each of the 2 to the power alpha t occupied vertices. Hence, we must be able to pack 2 to the power alpha t non-overlapping sphere in beta t dimensional Hamming space with radius of each sphere beta t times PE. If PE is small, radius of the spheres will be small. Then we can have more spheres in Hamming space and less redundancy. For a given value of beta, alpha cannot be increased beyond a certain limit without causing spheres to overlap. Thus, we can say that the ratio alpha by beta should be less than some arbitrary quantity Cs, and it depends upon channel noise and transmitted power. For a binary symmetric channel, formula of Cs is given and it depends upon the value of error probability. So the channel capacity is defined as K times Cs. Here K is equal to the number of symbols being transmitted per second. This is equal to double of bandwidth for bandwidth limited channel, and it depends upon type of pulse shape used in line coding scheme. From the formula we can calculate that Cs is worst when the value of error probability is half or 0.5. For continuous channel, value of Cs is half log 1 plus s by n base 2, and thus for band limited channel it becomes b times log 1 plus s by n base 2 bits per second. For a typical telephone line, signal to noise ratio is 30 to 40 dB and bandwidth of the order of 3.4 kHz. Then we can calculate the channel capacity will be 28 kbps. It signifies that if the information rate will be less than 28 kbps, then we can achieve error-free communication of information. Communication channels are usually described by the type of input-output ensemble and are considered discrete or continuous accordingly. If input and output are discrete events, then channel is called discrete channel. And if input and output are continuous events, then it is called continuous channel. And by this way, we can define several other channels. So we learned that Shannon's result was based on the use of redundancy. It means that if we want error-free communication of information, then we need to transmit some redundant bits along with the information. We have seen that in source coding, our effort was to find an optimum source coder which should add minimum redundancy with the information. On the other hand, if we want our transmitted information to be robust against error in the presence of noise, we need to add redundancy with the information signal. So we need to add redundancy in a controlled manner to have error-free communication of information. In digital communication, we learned about two types of encoder. One is source coder and other is channel coder. The job of source coder is to obtain the efficient digital representation of the messages with minimum redundancy. A channel encoder introduced controlled amount of redundant bits with the message to detect and correct the errors. So there are two types of codes. One is block code and another is convolutional codes. We will learn about these two codes one by one. Convolutional codes are more powerful class of codes because these codes are able to take care of not only AWGN channel, that is additive white Gaussian noise channel, but also they can take care of other channels like burst error channel.